All right, hello everyone. My name is Trevor Brown, and I'm going to be one of your instructors for CS341 Algorithms in the Winter 21 term. The course is going to be co-taught with Anna Lubu. And the course website is right here. More about that in a little bit. Let me start off with a quick table of contents for what we're going to cover in this lecture video. We're going to touch on the course mechanics and then look at an overview of the course material, and then we're going to turn to a worked example of a problem that I've called Bentley's problem. You might know this also as the maximal subinterval problem. And we're going to walk through multiple solutions demonstrating different algorithmic design techniques that we're going to learn throughout the course. So let's turn our attention first to the course mechanics. So the course website here, so the usual address. You can find there the syllabus, calendar, policies, slides, assignments. So I recommend that you go take a look at the website and mark down the important dates for assignments and so on, because you don't want to be caught and end up missing deadlines because you didn't write them down. And in this course, it's really important that you try to keep up with the lectures because material really builds over time. So if you have trouble understanding material early on in the course and you don't nail it down, it's likely that you're going to end up having difficulty understanding the later material. So for example, if you don't understand divide and conquer algorithms very well, then you may have a hard time working your way through the necessary recurrence relations and the recursion background that really drives the intuition behind dynamic programming problems that we'll study later. And we're going to use Piazza, for the discussion in the course. So questions can be posted there. Preferably students will make some effort to answer each other's questions. We'll also have TAs devoting some time to questions there, and we'll of course be looking at questions there as instructors as well. We'll also be making announcements on Piazza, so this is really important. You should stay caught up to date with whatever's posted on Piazza, because we're going to assume that you've seen any announcements or assignment clarifications and so on that are posted there. So please, read Piazza and stay up to date. Talking for a second about assessments in the course. All sections of the course are going to have the same lectures, the same assignments, the same midterm, the same final. So you don't have to worry about any inconsistencies there. If you're going to have some severe problems that'll cause you to miss an assignment, please notify us as long as possible before the deadline. We're not going to be able to respond the same way to a request, the night of a deadline as we could to one that is a couple days in advance. So please, as soon as you know that there's some chance you're going to miss an assessment deadline, please let us know. And the midterm and final are going to be take-home exams for the course. I won't go into the nitty-gritty details of the grading scheme for the course in this video, because I think that's kind of pedantic and not super interesting, because you can just find those details on the website. So take a look at the website to see the grading scheme. And of course, if you have any questions about it, you can ask questions on Piazza. So the textbook for this course is Intro to Algorithms. It's the CLRS textbook that's very well known. So you're free to buy the textbook. There are places where you can get it, even used for cheap. But it turns out it's actually available for free via the library website. So if you're not the kind of person who needs a physical hard copy of the book to be able to make progress reading it, then you might want to check out the online copy on the library website. For this course, you're expected to know entire textbook sections as we list them on the course website next to the lectures. All of the material presented in lectures, unless we explicitly say you aren't responsible for it. So not only the material in the book, but also in the slides and anything discussed in the lectures. There are also, of course, discussion sections for the course. The purpose of these won't generally be to introduce new concepts, but rather to practice and reinforce existing concepts. I think at least that's the current plan. So we'll try to be clear about what you're responsible for knowing in there. In general, we're thinking of the discussion sections as optional. Okay, now let me talk about academic offenses for a moment. So, especially now that this is an online course, we have to be aware of the possibility of plagiarism. Be careful not to end up plagiarizing by accident. We generally are fine with, students discussing one-on-one with each other, having high-level discussions about general approaches to solving problems, even problems on assignments. Not, however, on take-home midterms or finals. You should not be discussing take-home midterms or finals with your fellow students. Those are absolutely things that you're supposed to do alone in isolation, demonstrating your own individual knowledge. For assignments, we're generally okay with you having high-level discussions with individual students. So don't have a huge group chat where you divide up problems, but you can have a buddy that you work with and chat about approaches to solving problems. Now, the typical recommendation that we make in this course is don't take written notes away from such discussions. Now, this is sort of funny if this is an online course in an online world, and you may very well only be having interactions with your friend online. And so it's a little bit hard to avoid taking away any written notes from discussions, especially if you're having these discussions in text form. And so the way that I would phrase this is this typical constraint, the way I would rephrase it for the online world is if this is a topic that you could talk about with someone in person, water cooler conversation, and you would not need a whiteboard to help walk through any equations or formulae or to write down any details or remember what's going on, then it's probably okay. If this is the kind of discussion where you would be using a whiteboard as an aid, you should not be having this discussion with your fellow student. So, try to keep the level of your discussion high enough that you're not fleshing out all the details, just discussing broad strokes of problem solving. And class-wide discussions, large group discussions of solutions is not okay, at least until the deadline is passed, at which point we'll be publishing solutions generally anyways, and you guys are fine to discuss your various approaches with one another. Okay, let's try to sketch out the road ahead in this course. I want to ask the question first, why is or should CS 341 be important for you? And the answer will probably be different for different students. From my perspective, algorithms is really at the heart of computer science. It often appears in later courses. Really, it dominates technical interviews. So if you master this material, you're going to make your interviews a lot easier. And designing algorithms can also be really creative work. It's useful for some of the more interesting jobs out there. So certainly in many of the jobs that you might take after university, you won't be implementing fundamental algorithms. But in some of the more interesting jobs that you could possibly find yourself doing, you may have to perhaps not develop new fundamental algorithms or implement existing fundamental algorithms, but find ways to tweak fundamental algorithms that already exist to serve some new purpose or to conform to the constraints that arise in some new setting. And a lot of really interesting work can arise there. And of course, it's a required course for all of CS, and you want to graduate. What's a computational problem? Because computational problems are largely what we're going to be talking about in this course. Informally, it's a description of input and a description of the desired output. And an algorithm is, informally, a well-defined procedure or a sequence of steps to solve that computational problem, to take the input and produce some output. So an algorithm is what sits between the input and output. And there are different algorithms of varying levels of performance. So we can make faster and faster algorithms with better and better performance properties. And then, of course, there's also the question of algorithmic correctness. So some algorithms might not be correct at all. Okay, let me give you a few examples of computational problems that you might want to solve. So here's some fundamental ones. We have sorting, where the input is an array of integers in arbitrary order, and the desired output is the same array of integers in increasing order. And so you have these nice sorting algorithms, which I'm sure you guys have seen before in CS240 and other, probably you've seen some initial sorting algorithms in the first CS course you took as well. And then you have, for example, matrix multiplication, where you have two n by n matrices, let's say, A and B, and the output is a matrix C, that's the product of A and B. And then we might have, as a more subtle example, the traveling salesman problem, where you take as input a set S of cities and distances between each pair of cities. This doesn't necessarily have to be a strongly connected graph, but in my diagram here it is. And your output is the shortest possible path that visits each city and returns to the origin city. And so, this is a problem that sees applications in, for example, package delivery, scheduling the order of destinations for, food delivery like Uber Eats and so on. Okay, and these problems can have really vastly different complexities, and we want to analyze solutions to these problems to determine how good they are. So every software program that you write uses resources of some kind, right? So there are different kinds of resources. There are CPU instructions. We typically refer to CPU instructions as time. Okay, technically, not all instructions take the same amount of time to execute. Some instructions are more pipelinable than others. But in order to avoid really complicating our analysis, we tend to treat all instructions as if they're the same and take unit time. And so we just call this time analysis, runtime analysis. The amount of memory that a program uses, well, by memory I mean RAM, not necessarily disk space, although that could be considered to be a resource as well. RAM we tend to call space usage. And of course there are many other resources that we might care about. In this course we won't typically talk about them, but some other resources that you might talk about in other courses include I/O, network bandwidth, messages, locks and synchronization overheads for concurrent software, and so on. Now, analysis is the study of how many resources, or to what degree an algorithm uses resources. And usually we do analysis using big O notation to ignore constant factors, because constant factors are less interesting than the way that the complexity of the algorithm changes as we increase the problem size, because today we have a particular problem size that we want to solve, and in the future we might have a much larger problem size that we want to solve. And whether or not we'll be able to scale a particular algorithm out to work for us in future, or whether we have to design a new algorithm altogether, is really a function of how the complexity changes as the input size grows, assuming that our input sizes, our demands that we place on our software algorithms, increase over time. And we can, broadly speaking, divide our algorithms into a taxonomy of serial versus parallel, deterministic versus randomized, exact versus approximate, and so on. And in this course, we're really only going to talk about one small slice of the algorithmic landscape. Let me explain to you sort of where that slice of the landscape sits in the overall landscape. So let's talk first about serial versus parallel or concurrent algorithms. In a serial algorithm, you have a single thread of execution that's executing one instruction at a time. In a parallel or concurrent algorithm, you have multiple threads of execution that are executing multiple instructions at the same time concurrently. And then there's this question of deterministic versus randomized. So a deterministic algorithm always produces the same output when you give it the same input. So if you repeatedly run a deterministic algorithm on the same input, it's always going to perform the same sequence of steps and produce the same output. And a randomized algorithm is a little bit different. So there are different ways of doing randomization. You can actually do randomized algorithms that produce deterministic output, but take a meandering path to get there. But for this course, I'm going to define a randomized algorithm as one that on multiple runs of the same input might produce different outputs. So, for example, you could flip a coin, generate a random number, and then base your next action on the result of that. Now, of course, if you're talking about a random number generation algorithm that uses a seed as an input, you have to vary the seed, or else that random number generation algorithm is actually deterministic. So you have to be a little bit careful talking about randomization. And then there's a question of exact versus approximate solutions to problems. So exact algorithms produce an exact solution to the problem, usually an optimal solution to a problem. And an approximate algorithm typically produces something that's close to a solution. So for example, if you're trying to approximate the area under the curve on the right in this animated diagram, you could imagine an algorithm that iteratively refines a discrete approximation until the result has a sufficiently small error, and then you stop and call it a day. Now in this course, we're typically going to cover serial, deterministic, exact algorithms. Although, if we have time for a bonus lecture at the end of the course, perhaps Anna, who will be taking over for me halfway through the course and the lectures, will cover some algorithms that explore some other interesting niche in this landscape. Now, up until now in this lecture, I've been talking about problems for which we can come up with solutions, but tractability is the question of whether all problems actually have fast solutions, whether it's possible to solve all problems efficiently, or indeed whether it's possible to solve them at all. So for some problems, such as the traveling salesman problem that we saw earlier, we've only found exponential time algorithms so far. Well, wait a minute. That seems like a pretty practical problem that a lot of companies are solving at scale for things like, delivery drivers. How are they solving this problem at scale with maybe 100 deliveries in a day for each truck when we only know exponential time algorithms? Well, we only know exponential time exact algorithms, and there are actually fast approximation algorithms that can provably produce a result that is some constant times some constant fraction off from the optimal solution. So you might travel more distance than necessary, but maybe only 1.5 times the optimal distance. And of course, we have to sacrifice the precision of our solution in order to obtain a solution that we can get in time to schedule the trucks and send them out. So there are some problems where we've tried for a long time to find solutions to these problems, and we've been unable to find fast solutions. And we think perhaps there may only be exponential time algorithms to solve this problem. So these algorithms are really inefficient. In the case of the traveling salesman problem, to give you some informal idea of what exponential time really means, adding one stop on your delivery route doubles the runtime to pre-compute the optimal route. So, this becomes incredibly infeasible as, if a two-stop route takes 1 second, then a 100-stop route takes, an amount of time that would result in all of the stars in the universe burning out and being absorbed by black holes. So this really severely limits our ability to solve real-world inputs. So, tractability is really the question of whether there is a way around this limitation, or, crucially, should we stop trying and really focus our energy on approximation algorithms? And so one of the biggest, or at least most popular open questions in tractability is the question of P versus NP, which, phrased really informally, and of course we'll get into this later in the course more formally, it's the question of whether it's possible to solve such problems in polynomial time, or whether some of these problems perhaps cannot be solved in polynomial time, really have to be solved in exponential time. Good news, everyone. So right as I was in the middle of teaching, my new Logitech Brio camera arrived. So for the rest of the video, you guys get to actually see my face. Okay, so let's talk briefly about the topics that we're going to cover in the course. So on one hand, we're going to talk about fundamental and fast algorithms to tractable problems. So these are problems that we know how to come up with fast solutions to. These are typical algorithms, some of which you've probably heard of before, like merge sort, and some of which, like Strassen's matrix multiplication, you probably haven't. We're also going to talk about some graph algorithms. So, for example, breadth first search and depth first search, which you guys have probably learned before. We're going to talk about, Dijkstra's single source shortest path algorithm for finding the shortest path through a weighted graph. We're also going to talk about probably some others like Bellman-Ford. And then for all pairs shortest paths, we're going to talk about Floyd-Warshall. And for constructing minimum spanning trees, we have, I'm not sure yet which it'll be, either Kruskal's algorithm or Prim's algorithm. And then we're going to talk about topological sort for sort of pulling apart and ordering the dependencies in a graph that represents dependencies. And there are lots of other algorithms that we're going to cover. This is just a small sampling of fundamental algorithms that I wanted to mention explicitly. Crucially, we're going to cover common algorithmic design paradigms. So I think it's not just important to understand, sort of a standard set of fundamental algorithms that we all agree in computer science are important and are helpful for demonstrating useful algorithmic techniques. It's useful to build up that toolkit of algorithmic techniques and to get exposure to a lot of different algorithmic design techniques. But all of these algorithms, to one degree or another, fall into one or two of these common algorithmic design paradigms, which are really important to get a handle on if you want to do any sort of designing of algorithms, or maybe modifying or extending of existing algorithms, adapting them to suit new purposes. So a couple of the design paradigms we're going to consider are divide and conquer, greedy techniques. So divide and conquer techniques try to divide up a solution recursively into a problem into smaller subproblems, and then rely on the recursive algorithm to solve the smaller subproblems, and the creativity comes in as you're combining the solutions to smaller subproblems into a solution to the whole problem. Greedy doesn't explore, it's somehow greedy about its approach. It takes steps as you're trending towards a solution that seem like the right thing to do given only local information, sort of restricted information about the problem space that you're trying to solve. So you don't explore all possible solutions, and you don't explore all of the possible decisions you could make at any given point in time to pick the most optimal one. You pick some next step to take in solving your problem according to whatever seems best, according to some heuristic. And that's why we call it greedy, because it's just a heuristic method for choosing the next step that we're going to take towards our solution. We're sort of incrementally building up a solution heuristically, and proving that that local heuristic yields an optimal solution is usually the tricky part in these algorithms. So these algorithms are typically very simple, and they're proofs of optimality. Usually we're solving optimality problems, optimization problems with greedy. Those proofs are usually the subtle part. We're also going to look at dynamic programming, which is typically not greedy in the sense that we are always exploring all possible ways of picking our next element to add to our solution. We're looking at all ways of picking the next step to build towards an optimal solution, and we're picking the most optimal. So our solution is going to rely not on local heuristic decisions, but on sort of a careful, systematic exploration of all possible decisions we could make, and we're going to pick the one that's provably optimal. So dynamic programming is usually, the algorithms are a little bit more subtle to come up with. I think the algorithms are a little bit more subtle than greedy, but the proofs are a little bit more straightforward. And I would say dynamic programming shares elements of both divide and conquer and greedy, and it's kind of an interesting paradigm. Then we're also going to look perhaps briefly at exhaustive search or brute force, but I'm not sure if we'll get there. So exhaustive search or brute force algorithms are usually the sorts of algorithms that you would come up with if you hadn't put a lot of study into algorithmics. Because these are sort of the most obvious solutions that jump out at you. Try all possible solutions, and once you've tried all possible solutions, you're able to pick the one that is optimal. We're also going to put some time into studying mathematical tools for analyzing algorithms, because it's one thing to come up with an algorithm and then prove that it solves the problem correctly. It's another thing entirely to be able to reason to yourself or to others that your solution will run fast enough, or will consume a small enough amount of memory that you'll be able to run it and get a solution in a reasonable time or using reasonable computing hardware. So we're going to study a whole bunch of different tools for analyzing algorithms. Big O notation, of course, you guys have learned before, but we'll recaps and a little bit and extend your knowledge, perhaps of Big O notation, introducing things like little omega and little o. We're also going to study techniques for solving recurrence relations, which are a type of mathematical tool that makes it feasible to analyze algorithms that are more sophisticated than just a bunch of loops and straight line code. So algorithms that involve recursion, for example, you need tools like the recursion tree method, or the substitution method, or the master method for solving the recurrence relations that describe their complexities. And then we're going to analyze some tools for helping us prove that our greedy algorithms are optimal, such as exchange arguments and greedy stays ahead arguments. And then towards the end of the course, we're going to be studying intractable problems. We're going to look very carefully at the P versus NP, so the class P of problems that are solvable in polytime versus the class NP that are solvable in non-deterministic polytime. So we're going to study those two classes and study a bunch of example problems that fit into these different classes of problems. We're going to study polytime reductions, which are ways of showing that if you can solve one problem in polytime, you can solve another problem in polytime by using a solution to the first one as a black box. And we're going to study the question of decidability, whether a problem actually has a solution, whether it's decidable. So what do, at least I hope, you'll be able to take away from CS341? So you're coming into CS341 with a considerable amount of knowledge in CS. You've studied courses like CS240, you've studied data structures, maybe you've studied a bunch of math, a bunch of electives, but until you've done a really detailed study of algorithmics, I think you're like this egg that's got a bite out of you. You're missing a piece. And so my hope is that CS341 will complete your egg. You'll walk away with knowledge of a collection of fundamental algorithms that it just so happens you might also be asked about questions about in job interviews, so that's nice. You'll also walk away with knowledge of fundamental design paradigms, which are going to be useful for building your own algorithms, or perhaps adapting existing algorithms, or perhaps just in recognizing broad patterns that'll help you categorize possible problems that you'd like to solve and relate them to existing classes of problems that you've seen solved in similar ways. And also you'll walk away with a study of tractability versus intractability. And this is kind of nice because even working in industry, it's surprisingly easy to come across problems that you really want to solve, but it turns out they actually are impossible to solve, at least if you want an exact solution. Okay, I shouldn't say they're, okay, let me rephrase. So there are some problems that are impossible to solve, and being able to identify that this is a type of problem that's impossible to solve exactly is really nice, because you don't want to toil away forever trying to solve it, when really you should just be able to identify that you can't possibly solve it, and exactly, and try to find some approximate way to solve it. On the other hand, there are problems that can be solved just inefficiently, and maybe somebody who's incredibly intelligent years from now will find a way to solve these problems in sub-exponential time, but certainly no one currently living knows how to solve these problems in sub-exponential time. And we sort of suspect that they're not solvable in sub-exponential time, or else very surprising things would be true about our universe. And for these problems, again, you'd like to be able to identify that the problem you're trying to solve is, in fact, one of these problems, one of these so-called NP-complete or NP-hard problems, or that it's a problem that could be reduced to an NP, or that an NP-complete problem could be reduced to. So if you could solve this problem, you could also solve an NP-complete problem, which is a very strong evidence that this problem is very hard, and perhaps you shouldn't toil away for years working on it. At least unless you're hoping you'll be that genius who will crack the question of whether P is equal to NP. Okay, so these are nice things that you'll be able to walk away with. And, it can't hurt to have a bunch of mathematical techniques for algorithm analysis under your belt as well, because when you write an algorithm, it's nice to be able to quickly do some back-of-the-envelope calculations and argue to yourself that this will either take 10 seconds or 5 years to run. So I'm hoping that you'll walk away a happy egg with all of this stuff under your belt, feeling nice and confident that you'll be able to apply algorithmic techniques in the real world. Time for a coffee break. One of the nice things about preparing lectures online. Okay, so enough of the preliminaries and background. Let's talk about Bentley's problem. Let's do this worked example so we can try to demonstrate a few of the algorithmic design paradigms that we talked about in the previous slide. So what's Bentley's problem? Well, you're given as input an array of n integers, a1 up to an, and you want to find the maximum sum of consecutive entries of a. Okay, so let's go through a couple examples to demonstrate this. So here's an array. I've drawn the array indices in the bottom. I've numbered the array indices starting at 1 just because even in practice, if they typically start at 0, in theory they often start at 1 to make the notation more convenient. Call me a monster if you must. So here we have an example array containing 1, 7, 4, 0, 2, 1, 3, 1. And these are all non-negative integers, right? So what's the maximum sum of consecutive entries of A? Well, clearly it's the whole thing. So we just sum them all up. 19 is the answer. Here's another example where all the entries are negative. And in this case, the maximum sum of consecutive entries is the sum of no entries at all. Just don't take any of them. The solution is 0. Okay, here's a more nuanced example. Here we have 1, negative 7, 4, 0, 2, negative 1, 3, negative 1. Okay, so we don't want to include this 1 in the sum because 1 is clearly not the maximum. We could just take 4 or 4, 0, 2, and that's 6. Really, if we include this 1, we're going to have to get any more numbers, we're going to have to include this negative 7, which seems quite nasty. So 402 gets us 6, and we can decrease that to 5 by taking this negative 1 and increase it again to 8. So that turns out to be optimal. It's fairly easy to see. 402, negative 1, 3. So the solution is 8. And in these really small worked examples, it's pretty easy to see what the optimal solution is. But in much larger examples, if you have, a billion, if n is a billion or 10 billion, all of a sudden it becomes quite difficult to decide what the maximum sum is. Okay, so if I asked you to solve this problem, if you want to pause the video and just try to solve this problem briefly by yourself, maybe start out with just the absolute simplest solution you could possibly think of. So try to come up with the simplest solution you could possibly think of, and what runtime do you get? So I'll wait a moment for you guys to pause if you're interested in doing this little exercise. Okay, so I'm going to assume if you wanted to pause, you've done so. Let's see a brute force solution to this problem. So this is really the simplest thing you could imagine. All we're going to do is we're going to try every possible subinterval of the array, right? Because that's really what we're doing. We're taking the sum of consecutive entries, so that's picking a subinterval of the array from I to j for some I and some j, and summing up all the entries between I and j, and then we're going to just do that for all possible subintervals, and then figure out which one gives us the largest sum. So all combinations of I and j, where j is greater than or equal to I, and we're going to then, for each choice of I and j, we're going to sum up overall k from I to j. Okay, so here's the, pick an I and j. Over all the k between I and j, we sum up all the entries, and that gives us a candidate sum. So this is our pseudocode for this, quite straightforward. Initially, we have a candidate maximum of 0. We're never going to return anything smaller than 0. And then we have these two for loops where we pick I and j. All possible choices of I and j starts at I, right? So we're not going to pick j to be before I. Okay? And then for each choice of I and j, we're just going to compute. We're just going to sum up for k equals I to j, so, obtain a sum that's the sum of all those ak. And then we're going to compare the sum to the maximum sum that we've observed so far. Okay, so I would guess this is probably pretty similar to what each of you came up with if you paused and did the little exercise to come up with a straightforward solution. I want to ask you, what's the runtime of this algorithm? So take a moment and pause the video if you want to answer that question, or maybe you can just answer it super quickly and don't need to pause. Okay, I'm going to assume that you've paused it if you want to do this exercise. So we have three for loops here, right? And they're all nested. So this is a for loop from I equals 1 to n. So clearly there are n iterations of this. There's a for loop from I to n. So well, this is a little bit trickier. We can't just say this is n iterations, right? But this is for half of these iterations for I equals 1 to n. So half of those iterations, in particular the ones from 1 to n over 2, that's half of the iterations of this I loop. For those iterations, I is at most n over 2, and the distance from n over 2 to n is n over 2. So even though this is a complicated expression, for j equals I to n, this is at least n over 2 iterations for half of these I iterations. So you're going to get something like n squared, order n squared iterations for these two loops, although it's a more complicated expression. So we'll talk a bit more about big O and how you do this analysis later, although I hope for a lot of you guys this is just old hat and you've done this in CS240 and you can answer this question fairly easily. Now for this I to j loop, it gets even more complicated, right? You can do the same sort of analysis that I did for these previous two loops to discover that all three of these loops taken together is actually order n cubed time. Okay, so can we come up with a slightly better algorithm for doing this? I mean, it sort of seems unnecessary to have this k loop, right? I mean, why do we have to sum up all of the possible entries between I and j? I mean, instead, as we're incrementing j over and over again, as we're exploring this second loop from j equals I to n, every time j increases, really what's happening is we're increasing the sum by a of j. So why not just improve our algorithm by getting rid of the k loop and just adding aj to the sum every time? So that gives us an n squared. Clearly this is better than order n cubed because we only have two loops and we're just doing constant work inside. So this ends up being n squared times. So this is still a brute force algorithm. We're still trying all possible pairs of I and j, such that j is greater than or equal to I. But we've shaved off a factor of n, so this makes it tractable to solve much, much, much larger problem sizes. So in a modern machine, we could feasibly solve for a problem size of maybe n equals 10 million with an n squared algorithm. It would take a long time to run, but it wouldn't take days. It would take minutes in a reasonably fast programming language. That might take a while using a Python list. Okay. Now we can do actually considerably better, it turns out, but we have to get into more sophisticated techniques than just brute force. So our third solution to Bentley's problem is going to be a divide and conquer solution. So what we're going to do is we're going to take our array and split it into two equally sized parts. So we're just cutting it in half. We have an array. Let's just assume, to make this analysis simple, that the array size is a power of 2. That way, every time we cut it in half, it's an even split. That's not necessary for this solution. I'm just doing it for the sake of making our discussion here straightforward. So we don't really have to think about, unequal sized halves. But it doesn't really enter the discussion. It's not important. You can just put it out of your mind. Okay, so our solution, if you think about it, once you split this up into two subarrays, a left half and a right half, the optimal solution, the optimal subinterval, either has to be entirely in the left half, or entirely in the right half, or it has to cross over the two arrays. It has to cross the partition line. And so this is going to induce three cases that we're going to solve in slightly different ways. So case one, if the optimal solution is entirely in the left half, as it is in this particular example, where you can see that the optimal solution is 9, minus 3, and 4. Okay, we're not going to make this solution any better by adding anything to the right because it's overwhelmingly negative, right? So 9, 3, negative 3, and 4, this is 10 is the optimal solution. It's right there in the left half, okay? There you go. And case 2, the optimal solution is entirely in the right half. Okay, fine, it's symmetric. I won't bother drawing it or giving an example. Case 3, the optimal solution crosses the partition between the two halves. So this is the example, this is an example where that's true. So in fact, we saw this example before. The optimal solution was 4, 0, 2, negative 1, 3, right? And that crosses over the middle partition. So we have these three cases. Now, the way we're going to solve this in the divide and conquer paradigm is we're going to recursively, given the array A, we're going to split it into two halves, L and R. We're going to recursively solve, just by making a recursive call, for the maximum subarray in the left half. We'll call that max L. We're going to recursively solve for the maximum subarray in the right half. We'll call that max R. And then we're going to do something creative and more sophisticated to find the maximum subarray that's going across the middle partition line, and we'll call that max M. And my claim is this finding of the maximum subarray going across the middle partition line can be done in linear time, order n time. And now the solution, as we argued, has to be one of these three cases, right? So it's going to be the max of max L, max R, and max M. We get max L and max R just from our recursive calls. We don't have to worry about them. If we solve this, if we figure out how to take those two solutions and combine them with some extra creativity into a solution to the whole problem, which is what we're doing by taking the max of these three things and calculating this maximum subarray going over the middle partition line, then we don't have to worry about how these recursive subproblems are solved. We assume that they're solved correctly, and we show that if they are solved correctly, under our assumption, then our combination of the solutions of the subproblems into a solution to the whole problem should also be correct. And that's what we're going to do here. So you can see if we have a correct solution for max L, a correct solution for max R, and we find max M ourselves in linear time, then we're going to be able to combine these three solutions in linear time into a solution. And then it's a little bit more sophisticated to calculate the runtime of the whole recursive algorithm. That requires techniques we're going to talk about over the next couple of lectures, but I'll give you the punchline that it's a fast algorithm. So let's see how we compute the maximum subarray going over the middle partition. So suppose we have this example that I showed in the previous slide where the optimal solution does cross over the middle partition. How can we find the maximum subarray going over the middle partition? Well, we could do so by trying all possible subarrays, all possible subintervals, but that would be slow. We want to do something more intelligent than that. We want this to take linear time. So here's the interesting insight that makes it possible for us to do this in linear time. We're going to find the I that maximizes the sum from I to n over 2. So I is going to be on the left half. So we're going to find an I in the left half that maximizes the sum from I up to n over 2. Okay? And we're going to want to do that efficiently in linear time. And then we're going to want to find a j that maximizes the sum over n over 2 plus 1 up to j. So j is going to be on the right half. Right, and we know we're looking for a subarray that goes over the middle partition. So I is going to be in the left half, and j is going to be in the right half. So that sort of restricts the sets of i's and j's that we have to check a little bit. Okay, so j is going to be on the right half. We're going to find the j that maximizes the sum on the right half. So we're finding the I that maximizes the sum on the left half from the middle going to the left. We're finding the j in the right half that maximizes the sum on the right half from the middle going to the right. Okay, and we can prove that A of I to j is the maximum subarray going over the middle partition, and I'll do that in the next slide, although it's not a particularly difficult argument. So how do we do how do we find I and j in linear time? Well, it's actually quite straightforward. We start at the middle, and we start iterating for I to the left. And as we go, we add we're gonna go for I equals n over 2 down to 1, right? And for each I that we explore, we're going to add A of I to the sum. And we're going to do this for each possible entry. So this is a single for loop. and we're going to remember what the maximum sum that we saw was, similar to our brute force solutions. But this is just one loop for I equals n over 2 down to 1, and we're using the same trick that we used to avoid that k loop where we were summing all the entries from a of I to a of j, where we're just, every time we explore a new I, we're adding a of I to the sum, and we're going to take the maximum sum. And we do the same thing on the other side for j. So that's how we find these two sums that maximize the sum on the left half and maximize the sum on the right half in linear time. Okay? Now let's prove that that is, in fact, the maximum subarray going across the middle partition. So why is a of I to j maximal? Suppose it isn't, to obtain a contradiction. Then there's some a I prime to j prime that crosses the partition and has a larger sum. If this sum from a of I prime to a of j prime is bigger than the sum of a of I to a of j, then either this sum on the left, L prime, is bigger than the sum L, or this sum on the right, R prime, is bigger than the sum R. If both of these are the same size or smaller, then this sum can't be bigger. The fact that this sum is bigger means either the left half has to be bigger than this left half, or this right half has to be bigger than this right half. But that's impossible because we just said that we're picking I such that L is the biggest sum you can get on the left. And J is yields the biggest sum that you can get on the right. So this is impossible. So this means we've obtained our contradiction, and a of I to j must be maximal. Okay, so let's see how to actually implement this algorithm. It's fairly straightforward. I reasoned about it already, but here's some pseudocode that I threw together on the left. And let's just walk through a quick example. This is a different example. I'm going to walk through the three different cases. So if we want to solve this divide and conquer problem, we first compute the size of the array A, that's n, and then we have this base case. Okay, so you always have a base case. If n equals 1, then we know what the maximum sum of the subarray is, right? If a of 1 is negative, then it's just 0. Otherwise, it's a of 1. That's the maximum sum for a single array element. Okay, so we solved the 1 case. Now for our recursive cases, we're going to solve for max L. So we'll do recursive call on the left half of the array, or we're going to solve for max R, and we're going to solve for max R next. We're going to do recursive call on the right half of the array. Then we're going to compute max M, and here's the computing max M procedure that I talked about. So we'll walk through these different techniques. So first, the recursive call on the left. It's going to find that the largest subarray on the left half is that. It's 10. And it's going to do a recursive call on the right half. The largest sum on the right half is going to just be 3. Okay, so max R is 3. And then it's going to compute, we're going to compute max M. Okay, so we're going to do this by computing max I here. So max I is going to be our sum on the left, and max J, I've given these names that I didn't give them on the previous slide. So max I is the maximum sum on the left here, and max J is the maximum sum on the right here. We're going to compute max J, which is, so negative 2 plus negative 5 plus 3, well, that's still negative. That's negative 7 plus 3 is negative 4. So it's actually better to take no elements here. So max J will just be 0. Okay, so max M is max I plus max J, which is 5. And now if we take the max of all three of these, which is what we do at the end here, we can see the max of 10, 3, and 5 is 10. So our algorithm correctly finds in this input that the maximum subarray is these first three elements, which happen to be entirely in the left half. So the first recursive call gave us the correct answer. And we'll do one other quick example here, where the maximum subarray is going to be the one that crosses the partition. You can probably already predict how this is going to work. We do, sorry about the misaligned arrows here, that's my mistake. I'll fix those before the slides are actually posted. So for our first recursive call, we find that the maximum subarray on the left is just 4. So max L is 4. The maximum subarray on the right is also 4. So max R, that's funny. Okay, I've made a mistake here. Sorry, this is supposed to be 4. I'll again fix that in the slides before I post. Then we compute max M, which is going to be, okay, so the sum to here is 0. The sum to here is 4, so okay, we should take 4. The sum to here is -3, that's definitely not the maximum. The sum to here is -2, that's definitely not the maximum. 4 is the maximum. And then calculating max j, to the right we have 2, 1, 4, 4. So 4 is the maximum on the right here. And then max m is going to be the sum of max I and max j, which is 8. And the max of 4, this should actually be a 4 here, and 8 is 8. So this correctly finds that the maximum is crossing the partition boundary here. Okay, now I didn't plot out the actual recursion that happens in these recursive calls, but it's not important, right? You guys understand recursive algorithms. Okay, so it turns out that this runs in order n log n time, and it's likely that at this point, the knowledge that you have in computer science so far hasn't actually equipped you to do this kind of analysis. If I asked you to analyze this function, you probably wouldn't have the mathematical tools that you need to do so. So this is something that you're going to gain in this course, the ability to actually do the runtime analysis on this algorithm. So we need new mathematical techniques. This is where recurrence relations, the recursion tree method, and the master theorem are going to come in. So this result is actually quite good. Right? N log n, you can run this for enormous problem sizes, right? This is about as efficient as sorting. But can we do better? And when I say better, really I mean asymptotically better. Okay, finally, let's see a solution for Bentley's problem based off of dynamic programming. So this solution is going to seem perhaps a little bit strange or a little bit magical even at first, but it's, this is because it's pretty hard to get into this stuff without really diving into what dynamic programming is, but I'm going to do my best to give a, no dependencies description of how this algorithm works. Hopefully this description will make sense. If it doesn't, don't worry if dynamic programming seems a little bit magical at first. When we eventually cover dynamic programming, hopefully you'll see enough examples that it'll start to make sense to you. Okay, so what we're going to do is we're going to define two functions, which will really be recurrence relations. We're going to make these two definitions. So we're going to define include j, and then we're going to define exclude j in a moment. So we're going to define include j to be, this is a mathematical object, we're defining it to be the maximum sum of consecutive entries in the array 1 to j. So it's a subarray, right? We're considering a restricted prefix of the array. We're restricting our attention to the prefix of the array from 1 to j, and we're asking what's the maximum sum of consecutive entries in that subarray if the sum must include the last element aj. Okay, and remember, it's consecutive entries. So what this means is the sum is going to include aj, and so it's either going to be aj itself, or it's going to be aj and then some number of elements before that, right? So it's some suffix of the array a1 to j. Okay, and it's in particular the maximal. It's the suffix that maximizes the sum of entries. Now exclude j is the maximum sum of consecutive entries in the array 1 to j, so it's the same restricted subarray, but the sum must exclude a of j. So this is the best you can do if you don't use a of j. So include j is the best you can do if you include a of j, and exclude j is the best you can do if you exclude a of j. Okay, so we're just defining these two mathematical objects for all j, for all j from 1 to n. Now observe, if we had a way of solving for include j and exclude j for all j, then the solution to our problem would just be the max of include n and exclude n. Because think about it, include n is the maximum sum of consecutive entries in the entire array if the sum must include a of n, the last element. And exclude n is the maximum sum of consecutive entries in the entire array if the sum must exclude a of n. This represents both possibilities, right? So include of n is the best you can do if you include a of n, and exclude n is the best you can do if you exclude a of n. So the best you could do for any sum of consecutive entries in the entire array would just be the max of include n and exclude n, okay? Now, the question, of course, is how can we efficiently compute include j and exclude j for all j? Well, we can define recurrence relations to solve for include and exclude. And here's how we're going to define them. So let's look at a base case first. These are recurrence relations. So at the bottom of the recurrence, there's a base case. So include of 1 is the best we can do with the array a of 1 to 1. So just the single element a of 1, if we must include in the sum a of 1. Well, that's just a of 1, right? And exclude 1 is the best we can do using for the sum of a subinterval of the array a 1 to 1 if we exclude a of 1. Well, that's just 0. Okay, that's the base case. Now what about the recursive case? Well, include of j is going to be it's going to break down into two possibilities, right? So that there are two possibilities. Either we're going to start a new sum of consecutive entries starting at aj, or we're extending the best sum that ends at a of j minus 1. So those are going to be our two possibilities. And these are really the only possibilities for an optimal solution to include j. Remember, include j has to be the maximum sum we can get using the array prefix a1 to j using a subinterval of that array prefix. And in particular, we have to include a of j, so it has to be a suffix. So either there's some sum that we're going to extend using a of j, or we're going to start a new sum starting at a of j. Okay, so either it's going to be a of j, or it's going to be a of j plus include of j minus 1. Include of j minus 1 is the best we can do using the elements a of 1 to j minus 1 if we have to include a of j minus 1. And so this is going to be a sum that includes a of j minus 1. We're going to add a of j to it. So that's still going to be consecutive elements included in the sum. Those are the two possibilities for include of j. It might take you a moment to absorb that. Perhaps take a moment to think about it. You can pause and think about it if you like. And I will go through an example after this. Now exclude. If we're excluding a of j, then the best we can do using the elements in a of 1 to j is simply the best we can do using the elements a of 1 to j minus 1, because we're not using element a of j. So what's the best we can do using the elements a of 1 to j minus 1? Well, it's the max of include a of j minus 1 and exclude j minus 1. Okay, so this is the best we can do using all of the elements except for aj. Okay, now we can compute these two. So that's defining these recurrence relations, which I claim implement the defined mathematical objects that I introduced a couple slides back. So I claim that this recurrence relation is a solution, a mathematical solution, to produce the mathematical objects that we desired on the previous slide. Now we can actually compute these numbers using two arrays. So if you recall the base case and include j definition, right, and recall the definition here, I'm going to show you how we can compute these recurrence relations. Okay, so here we have A, the source array, and here we have the include array. So include 1 should be the maximum solution in A 1 to 1 that includes A of 1. Okay, well, that's just 1. Include 2 is going to be the max solution in A 1 to 2 that includes A2. Okay, and we've said this is how we're going to solve that. We claim that this is a solution that produces this mathematical object with this definition. So how do we actually implement this? Well, the first slot, we're just going to plug in a of 1. The second slot of include, we're going to take the max of a of 2, which is negative 7, and a of 2, negative 7, plus include of j minus 1, which is the best we could do with the sum for a sum of the array A1 to 1, including element A1. So that's going to be -7 plus 1, here include of j minus 1. Okay, so we're just going to fill in the array like this. We're going to keep using this recurrence relation to just fill in the array. Eventually we fill the whole array up, so you can double check that these numbers make sense. It's a good exercise too. That's how we compute include of j. Now, to compute exclude of j, we have our base case. Exclude of 1 is 0. And then exclude of 2, 3, 4, 5, we're going to fill in using this recurrence relation, okay? So we're going to fill in include first, because it just depends on earlier elements of its own array, whereas exclude depends on include. So we're going to fill in exclude after we fill in include, the relevant include entry. So you can see exclude of j depends on include of j minus 1 and exclude of j minus 1. Okay, so slot 0 is just going to be 0, according to the definition. Slot 1 is going to be the max of include 0 and exclude 0, which is 1, right? And exclude 2 is going to be the max of include 1 and exclude 1, which is 1. And this continues. You can double check these numbers. And eventually we have include n and exclude n. And we can see that the max of these two, 8, ends up being the solution to the whole problem. Okay, so if we want to turn these recurrence relations into code, basically turning what I just, the algorithm I just walked through into code, it's pretty simple. You define two arrays, exclude and include. You initialize them with the base case, and then you have this for loop for j equals 2 up to n. We just repeatedly assign exclude j and include j, alternating. It doesn't particularly matter that these two are in the same loop. I could have done them in different loops. I could have done the include loop first because it doesn't actually depend on exclude at all. It's just important that include j minus 1 is done before exclude j, because exclude j needs include j minus 1 to be finished. But that's fine because we're just computing this in a loop. Every time we compute j, the j minus 1 has already been computed. And at the end, we return the max of exclude n and include n. Okay, now, do we actually need these arrays? Okay, in the recurrence relation, it is a very direct translation from the recurrence relation to arrays, but do we actually need the arrays? When we're computing exclude j and include j, we only need the j minus 1th element of each of these arrays, right? We only need the last element. And at the end, the answer that we return only needs the last element, right? So it sort of sounds like maybe we could get away with using only the last element, keeping only the last element. So we can create a more space-efficient version of this algorithm by basically getting rid of the arrays, the array subscripts, and semantically, at the time that we compute exclude j, we want the include variable to represent include j minus 1. And it does. At this point, you can verify, as an exercise, that at this moment in the algorithm, this include variable semantically contains include j minus 1, and this exclude variable semantically contains exclude j minus 1, and this include variable semantically contains include j minus 1. And then after these assignments, these semantically contain exclude j and include j. So at the end of the loop, this contains exclude n, and this contains include n. So the algorithm will perform exactly the same sequence of steps and produce the same values, but we're only using two variables. So this has only constant space overhead over top of the input array. So this is a super efficient solution. What's the runtime on this? If you want to take a moment to pause and answer, I'll give you a second to do that. Okay, so the runtime for this is linear. So you can actually solve this problem in linear runtime and only constant added space beyond the input. Now, how do these algorithms actually perform in practice? Because we've talked about their theoretical runtime complexities, but sometimes the theoretical runtime complexities, because they hide constant factors, don't accurately portray how long it actually takes to run these things on a real system. And so here we actually have performance results, some of which are real numbers and some of which are extrapolated. These are run on a real system. Now these were run on a Pentium 2, so I didn't run these numbers. People who taught this course before I did ran these numbers. And Pentium 2 is a pretty old system. This is like circa 1997. So we've come a long way since then, but you can still see that these numbers, or the extrapolated numbers, suggest that no matter how much technology's progressed since then, you still can't meaningfully solve large problem sizes with, an n cubed algorithm for the solution, the first solution, because, 10 million elements takes 140,000 years to compute in this extrapolation. So we can see the fact that it takes 140,000 years for solution 1 and 4.2 seconds for solution 4 means that the algorithmics here really matter a lot. But there's also another point you could make, that the n log n solution might be good enough. Maybe you don't necessarily have to push that last mile to get the most efficient solution possible in terms of asymptotic complexity. Sometimes something is not optimal, but is close enough is sort of good enough in practice. So n log n is actually pretty reasonable. Okay, but how about a more modern system? Ever since I started teaching this course 3 years ago, I've been really curious to know how these results would change if you ran it on a system that wasn't 25 years old. So I actually ended up coding this up. I coded up all 4 algorithms and a couple extra variants of them over about 35 minutes. And I prepared a time lapse. So, well, if you're curious to see it, you can stick around, and otherwise consider the mandatory content for this lecture finished. See you guys.